Okay, lab one, we'll do a hands-on lab on the topic of facility, water, and personnel validation that are required for the parental drug manufacturing. So all these are part of the CGMP requirement, as we talked about these in the lecture. Okay, so before you start the lab, so I want you to work as a group of maybe 2 or 4 members. Depends on what lab we're gonna run. Depends on the instrument situation. Sometimes you can work as a group of 2, or sometimes if we don't have enough instruments, you may have to work in a group of 4. So I will tell you what kind of group I need you to make. Depends on the lab. But I want you to find a lab partner while you're working in the lab. Hopefully, at least one of you will be a more experienced lab partner, so who have done many hands-on labs already. So the experienced lab partner can guide and help the inexperienced lab partner. So I know at least that some of you have done so many hands-on lab courses like 211, 212, 201. So if you are one of those students, please find a partner who hasn't done many of those courses, because this course is typically a mixture of experienced and inexperienced students. So for the efficiency of the lab, I want you to find the partner so you can complement each other. Okay, so before we get started, I want you to make sure you have some background lab skills. For example, aseptic techniques. I know some of you haven't done any hands-on labs. This may be the first course with the lab, right? That's fine, but I want you to understand at least the importance of these techniques. Number one is aseptic technique. So what does that mean, aseptic technique? It's a technique that prevents any contamination during your process, right? So there are ways of carrying out your lab procedure, maybe by putting on your PPEs, gloves, sometimes the safety goggles, sometimes face masks, and you may operate under the biosafety hood in a particular manner. So understand that may be the part of requirements in many labs. And then scientific lab measurement skills. Okay, and measurements meaning you need to be able to measure out a very scientifically defined quantity. That quantity may be in a weight or volume or maybe pH, or depends on what you're going to be dealing with, right? So for example, if you are dealing with the volume measurements, you may be dealing with micropipettings or micropipetters, right? Do you know how to do that? If you don't know, I can show you while we are working in the lab, or your lab partner can help you as well. Okay, and then if it's a weight measurement, you may be able to use balances, analytical balances, or different kinds. Do you know how to calibrate your balance and how you understand that? Maybe pH meter, same way. Okay, so hopefully you and your partner can work together. I will be around as well, and if you are not familiar with this, we'll have a chance to learn all these. Okay. So when you talk about what conditions, what environments are required in terms of manufacturing maybe injectable drugs, parenteral drugs, okay, there are so many different layers of requirements, of course. The building where the manufacturing is taking place, it should have a special design, as you know, right? And you may need to have a clean room space, and you may have to have all those instruments, manufacturing instruments should be cleaned and validated, and personnel working in there should be all trained and validated, right? And the materials that you are using for your drug manufacturing should be all validated in good condition as well. So one of the main materials you'll be using a lot in your manufacturing is actually water, right? So then what kind of water can you use for your CGMP manufacturing? So of course you cannot use tap water straight out of the water spigot, right? You have to use very qualified clean water. So the water you can use for your drug manufacturing is actually specified. Okay, it should meet the requirement that's set up by the FDA, of course. Okay, there are different standards in terms of water specification. For example, U.S. Pharmacopoeia says the good water should have these requirements, or European Pharmacopoeia also says some of similar requirements as well. Okay, so if you look at some of those requirements, okay, the inorganic content, maybe the contaminants, should be a very small quantity. Then how do you measure the inorganic content? If you measure it, you need to be able to use the conductivity measurement. Okay, because some of those inorganic materials are kind of metallic, charged electric conducting materials. So if you have a lot of those, the conductivity would go up. If you don't have a lot of those, conductivity will be staying very low level. So you can measure that. So the conductivity, if you measure it, should be less than 1.3 microsiemens per centimeter. Okay, and then the organic content, of course, the contaminants made with organic material, carbon compounds, they should be less than this much, 0.5 milligram per every liter of water. So very little amount of organic compound is allowed. And then importantly, the pyrogen content. Pyrogen, again, what is what? Again, it's endotoxin. Those are what? The broken debris of cell wall material of gram-negative bacterial cells. Okay, that should be very little. So how do you quantify that? You use LAL assay. We talked about it in the lecture. So the assay is using limulus amebocyte lysate. That's the what? Horseshoe crab blood cells, and they will coagulate. So you can use the test to quantify the amount of endotoxin. So through the test, you have to prove that there's less than 0.25 endotoxin unit, EU stands for endotoxin unit, per every 1 ml of water. Okay, and then microbial content. If you sample some of your water and plate it on the in a petri dish, and there are something called CFU. CFU stands for what? Colony forming unit, actually made up of a single cell, bacterial cell. So in every 100 ml of your water, there should be less than 10 bacterial cell present. That's a requirement. Okay, so you have to prove that your water that you are using meets all these requirements. How do you do that? By doing all the testing assays. Okay, who's going to do that? QC technicians will perform the test probably every maybe week or something like that. There's a required testing period. So it's part of the QC's job. Okay, so out of these testing assay methods, in this lab, you will do a pyrogen LAL assay test. Okay, so of course the pyrogen endotoxins are fever-inducing entities coming from bacterial debris. If they are injected going into the human body, they will cause sepsis, so people can die from it. Okay, so LAL stands for limulus amebocyte lysate. So they can bind with endotoxin and coagulate. Okay, so again, these are limulus amebocyte. The lysate, the blood cells, will be collected from these horseshoe crabs, and then if they bind with those endotoxins, okay, those broken debris of bacterial cell, and they will give you this gel formation. Okay, or if they are conjugated with the chromogenic substances, colorful substances, they will give you color that can be measured in the spectrophotometric assay, through the assay, so you can quantify them, okay, accurately. So that's the LAL assay. So LAL assay can be done quantitatively using maybe color-based detection method, or it can be done as qualitatively. If you use a gel clot formation, depends on gel clotting or non-clotting, you can quantify that there is enough endotoxin, not enough endotoxin. Okay, so between those, you're gonna try to do the gel clotting LAL assay. So some of you already have done this in your previous class, maybe 212 class. You've done it. So if that's the case, then maybe it's the second time. You can master it by doing one more time, especially with your partner who hasn't done it. So maybe you can be the leader who can guide the process and help your partner to go through this, because your partner may not even know how to hold the micropipette. So you can be a kind teacher or guidance for your lab partner. Okay. So anyway, the gel setup will be, you will have to set up two assays okay, in your LAL gel clad assay, as you remember. Okay, so first set will be used as a standard, if you remember, right? So there will be 6 total test tubes given. Those are blank test tubes made out of glass, okay? And those will be using very clean endotoxin-free test tubes that are expensive, okay? And you're gonna set up those test tubes in a very clean environment. So you'll have to walking in biosafety hood aseptically. So put on your gloves, clean up your biosafety hood, and put on your sleeve. Don't expose your naked skin. You have to cover your hands and your bare skin should not be exposed by putting on the sleeve, and then your hands and arms should be all sprayed. Okay. So in those endotoxin-free test tube, you will be also given with the endotoxin-free water that we purchase. Okay. So all these test tubes will be filled with about 0.1 milliliter of endotoxin-free water at the beginning. Okay. So you will be given it a bottle of endotoxin-free water. So you will be using a micropipetter to set up 0.1 ml, which is 100 microliter, and transfer that amount of water into in each test tube. So all these 6 tubes will have 0.1 ml of endotoxin-free water at the beginning, right? And then you will be also given with the endotoxin sample. Okay, those are pure endotoxin that's made. Okay, and that's diluted. So that endotoxin stock solution you'll be given with will have the concentration of 1 endotoxin per ml. Okay, and you're going to transfer that 1 endotoxin per ml, the stock, okay, into your test tube. Okay, let's say first one is blank, so you're not going to add endotoxin there. Okay, you're going to skip that. But from the second tube to the 6th, so these guys, okay, you're going to add endotoxin stock solution, okay, into there. So actually 0.1 milliliter, the same volume, okay, of endotoxin solution into the first tube, which is tube number 2. Okay, then how much are you going to get? So there was 0.1 ml of water in there, and you are adding 0.1 ml of endotoxin. So total 0.2 ml mixture will be generated, right? So after pipetting it, you will pipette up and down to mix those 2 solutions. So you'll have total 0.2 ml there, right? After doing that, you're going to transfer 0.1 ml out of 0.2 ml total from this tube number 2 to tube number 3. Okay, and pipette in, and again pipette up and down. So so before you pipette 0.1 ml out of the first tube, you're going to change your pipette tip. Okay, let's get a new tip and transfer 0.1 ml of the tube number 2 to tube number 3. Okay, and then mix it by pipetting up and down, and then you're going to have 0.2 ml here as well. And then at this time, your tube number 2 should not have 0.2 ml. Since it lost 0.1 ml, so it should have 0.1 ml there, right? So now your tube number 3 will have 0.2 ml. So you're going to mix them by pipetting up and down, and then change your pipette tip, and then transfer 0.1 ml from here to here again. Okay, so again, you only have 0.1 ml there left, and now this tube has 0.2 ml. So pipette up and down, mix them together, okay, and then change the tip and transfer again 0.1 ml from here to next tube. You do the same thing over and over, right? Okay, and then to the last tube. And this tube may have, I guess this diagram is a little different than this. Tube number 6 is not shown up there. So assume that there's another tube number 6 there. So you'll pipette 0.1 ml there, and you'll have 0.2 ml up and down, mix it. And then this tube, from there, you will discard 0.1 ml, take out, and discard it. So you'll have 5 tubes there, and if this is tube number 1, you're not going to add any endotoxin there. So actually, this diagram is missing one tube there. That's tube number 6. Does it make sense? Okay. So you're basically creating a serial deletion of all these tubes. That's what you are doing here. Okay. So serial deletion of endotoxin. Okay.